Right, now I'm going to attempt number 21 from your textbook in chapter 2. It's talking about a man that stands still from 0 to 5 minutes, and then from 5 minutes to 10 minutes he walks at a constant speed. And so it wants us to calculate some values of that for different intervals of time. It actually is interesting that in part E it asks us to sketch x versus t and v versus t and indicate how the answers through A through D can be attained to the graphs, which is kind of funny because my natural inclination is just to sketch this out. We did that several times in class. So I'm going to go ahead and do that at this time and see how that plays out. So I'm going to start off, because it's giving me information about the velocity, I'm going to start by sketching that out. So here is the velocity of this person with respect to time, and from 0 to 5 minutes there is none, and then from 5 minutes to 10 minutes it is some positive 2.2 meters per second. So there is no velocity here, it's just 0, and then it increases to 2.2 meters per second. Just very suddenly. Sketch that there, right? So that's his velocity. Not the world's most exciting graph, but that's what it looks like. And so we can sketch that. We could also sketch the position graph, right? We could sketch the acceleration, but that will look painfully boring because there is no real acceleration. Unless we assume there's some acceleration. I mean, obviously he's going from rest to some constant speed, but it doesn't tell us exactly where. It's a bit of an odd situation because at this moment he kind of has instantaneously an infinite amount of instantaneous acceleration. You can't really draw the tangent line on this particular curve, right? It's not really a curve. It's not a function at this point. So mathematically that would be something like a saddle point or some type of an odd point, right? It's not a function at this point, so that's kind of an interesting question. We'll see how that plays out. In terms of sketching, that's probably why it doesn't ask you to sketch the acceleration graph, right? The position graph would look something like this. We still have the same amount of time. The points of interest here are 5 minutes and 10 minutes. I should maybe label that a little clearly so it doesn't look like position meters. So again, from his position with respect to time is 0 because he's not moving at all, and then he begins to move, and so he is going to cover some amount of increasing distance like so, and the slope of that line, right, the slope of this line is going to be very straight because we know that the derivative of this line is going to be a constant value. And so we know what the value of this line is going to be. We know that the rate of this line is going to be equal to the change in displacement over the change in time, and that's going to be equal to 2.2 meters per second, because that's what the problem told us. That's between the intervals of 5 minutes, between 5 minutes and 10 minutes. Right? So the question asks us a little bit of something different. It says, what are his average velocity and average acceleration from the interval of 2 minutes to 8 minutes? Ah, I see, okay. So it wants to know about a time from here to here, which is kind of strange in both cases. Well, actually, it doesn't ask about the position. It asks about the velocity here. Oops, that's probably not quite 2 minutes, but we'll pretend. 2 minutes to 8 minutes. And we can already tell that's kind of a weird deal, but we would do the same thing, right? The average velocity, unlike the instantaneous velocity, is the change in position, the displacement, divided by the change in time. And so that's really, it wants to know between these 2 points, what is his average velocity? So his velocity here is 2.2 meters per second, and here it's 0. We can get that information from the position graph, right? We have here, this is 8 minutes, and he's at this position, and he was at a position of 0 at that time. We can get the slope of this line here will tell us the average velocity over this interval from 2 to 8 minutes. Okay? So we do need to know where he is at this particular point in order to be able to determine the average velocity. And that's a pretty easy quantity to figure out. We know that this is at 8 minutes, that is 3 minutes after he started moving, and he was going 2.2 meters per second. So if we want to know his position at time equal to 8 minutes, we simply need to multiply the velocity, the average velocity, which is 2.2 meters per second, times the change in time that we're interested at 2 minutes. Well, it's 2.2 meters per second at 8 minutes. So the change in time where he was actually traveling this speed is only 3 minutes, right? Because he started at 5 minutes, started moving, and stopped moving at 8 minutes. So that's going to be 2.2 meters per second times 3 minutes converted into seconds is going to be 180 seconds, right? So that tells us the position, and then we can use that information by what the position is, and we know the position here at time equals to 2 minutes is 0. So we can take the difference between these two things. So the average velocity between minutes 2 and 8 minutes is going to be equal to the displacement, which is equal to 2.2 meters per second times 180 seconds. Oops, there we go. That's what the position is at that point, minus 0 meters, which is the position at 2 minutes. And take that divided by the total change in time, which it's not just 3 minutes anymore. We want to know the interval over this full change in time here. If we use just 3 minutes, we'd get back exactly 2.2 meters per second. So the whole interval here is actually 2 minutes to 8 minutes is a total of 6 minutes, right? And converting minutes into seconds, so 6 minutes, we can convert that into seconds by multiplying it by 60 seconds per 1 minute. Right? Our minutes cancel out, and we know there's 360 seconds, and so we can divide through, and that'll be essentially, we get 2.2 meters per second divided by, times 180 seconds divided by 360 seconds is really the same thing as dividing by 2. This is 180, this is 360, so this is really going to be 1.1 meters per second. The seconds cancel here, and that the calculations, yeah, I even was able to do this without a calculator because everything canceled out really nicely. So we get the average velocity between 2 and 8 minutes is 1.1 meters per second. And if you notice, I'll do the average acceleration in the next step. But notice I included my units all the way along this calculation, and it was really helpful. The units ended up canceling out, and if you follow your equation carefully enough, everything should cancel out in the end. So that, well, everything except what you need. It turns out, without knowing that I needed a velocity here, I just plugged in the units as I needed to, and everything canceled out. Seconds divided by seconds gives us just 1. Right, so we're left with meters per second, which then we can use that as a check that, there's at least a pretty good chance we did the calculation carefully, as long as we kept all the numbers that we needed to, because we ended up with meters per second at the end, which turns out to match this average velocity. We didn't just write this down blindly. We got that through the calculation that we did on this side. All right, so I'm going to stop this now and start another one and talk about the average acceleration.